Welcome back to Precalculus. This is section 1.8, combinations of functions and composite functions. So in this section, we're going to learn how to perform operations on functions and find compositions and combinations of functions. More specifically, we're going to learn how to add, subtract, multiply, and divide functions, and then we will talk about composition of two or more functions. And so the first thing we're going to look at is just performing the basic operations now onto functions. Throughout your whole math career, you've done addition, subtraction, multiplication, and division, and now we're just going to go ahead and extend that onto the functions that we've been working with. So for the sum of two functions, you'll often see this notation f plus g of x, and all that means is take your function f and add on function g, and so essentially you're going to add up their common terms and simplify that new equation. And in a similar way, we can subtract functions. So f minus g of x just means take f of x and subtract g of x from it. And again, you're just going to essentially combine like terms through subtraction and simplify the resulting equation. Next, we have the product, which you're going to be using a lot of distribution and again combining like terms to simplify and create a new function that is the result of the two previous. And so in also division, so we'll be taking one function, dividing it by another function, and the only thing we're going to have to watch out for here is that our function that is in the denominator doesn't equal 0. And so to avoid that, we're just going to have to talk about some of the domain restrictions and write those out when we divide fractions. So let's say we have these two functions, f of x is equal to x squared and g of x is equal to 1 minus x. So for part A, we have to find the sum of these two functions. And so this is telling us we're just going to take our function f of x and add on the function g of x. And so f of x is just x squared, and on to that we're going to add 1 minus x. And for these problems, I do highly recommend that you use parentheses for each of your functions. That way you don't have any small mistakes later on. And so here what we would normally do is combine like terms, but in this case we don't really have any like terms. Here we have an x squared, here we have an x to the first, and we have a constant. So really all I'm going to do is just organize these in decreasing order of exponents. So I'm going to have x squared minus x plus 1. And so as you can see, when we add f of x and g of x together, we get a new function x squared minus x plus 1. And so similarly, when we subtract f and g, we're just going to take our function f, subtract function g, and so we're going to have x squared minus 1 minus x. And so in here, I would once again think about combining like terms, but in this case, I do not have any like terms. So I'm just going to go ahead and distribute that negative through, and we're going to get x squared minus 1 plus x, which I can then rearrange to get x squared plus x minus 1. And that is the result from subtracting our two functions. And so next we have multiplication. Now multiplication, once again, I'm just going to take my function f of x and multiply it by g of x. So this is actually going to work out exactly like the distributive property. So f of x is x squared, and so I have to multiply that to 1 minus x. And when I distribute into the parentheses, remember you got to go to each of the two terms. So x squared times 1 gives me x, and then x times negative x is going to be negative x to the third. And so finally, again, it's always better to write this in descending exponent order, so we can rewrite this as negative x to the third plus x squared. And so now for division is where we have to worry about our domain. So if we take f of x and divide it by g of x, we're going to have x squared divided by 1 minus x. And there isn't much simplifying you have to do for this problem, but you do have to think about the domain restrictions. So since we are dividing and we could potentially have a 0 in the denominator, we have to watch out for that one restriction. So 1 minus x, if I set that equal to 0, that's going to help figure out what x values would make this denominator 0. And so when I solve for x, I get x equals 1. And so what that tells me is x actually cannot equal 1 because that's what makes our denominator 0. And so the function we obtain when we divide f and g is just x squared divided by 1 minus x, as long as x is not equal to 1. And so the next thing we're going to look at is what's called composition of functions. And we show composition of functions with this notation here that has a small circle in the middle. And this notation would be read as f composed with g of x. And all that means is that we're going to plug in our function g into f. So wherever we have an x in our function f, we would be replacing that with whatever function g is. And so later on, we're also going to talk about the domain of the compositions. So here we got an example where f is the function 2x squared and g is 3 minus x. For part A, we want to find the composition of f of g. And so what that means is we're going to take our function f and plug in g of x into it. And we know g of x is 3 minus x, so essentially we're just going to have 3 minus x be the input for our function f. And all that tells me is wherever I see an x in my function f, I'm going to replace that with 3 minus x. So then we're going to have 2, and then instead of x, I'm going to go ahead and replace that with 3 minus x, quantity squared. And I could definitely go ahead and simplify this out a little bit, but for now I'm just going to go ahead and leave it like that. So if we look at the next problem, it says we have g composed of f of x. So what that means is instead of plugging g into f, we're going to plug in f into g. And so everywhere that I have an x in my function g, I'm going to actually replace that with 2x squared, which is f. So for g of f of x, I'm going to have 3 minus, and here again, instead of writing x for our g of x, I'm going to go ahead and put in f of x, so 2x squared. And we can simplify this a little bit, so 3 minus 2x squared. And again, I always recommend that you write in descending exponent order. So this is the same thing as negative 2x squared plus 3. And so for the next one, we're back at looking at f composed of g, except now we're actually going to evaluate this function which we had already found for part A at x is equal to negative 2. So if I copy over what we finished with for part A, I have 2 times the quantity 3 minus x squared. But this is saying instead of using an x, I'm actually going to go ahead and replace that with a negative 2. And so I can now simplify this out to get a numerical answer. So 3 minus negative 2 would be positive 2 squared, which would be 5 squared. And so we end up with 2 times 25, which is 50. So let's continue talking about function composition, but now let's also include the domain of this new function that is made up or composed from f and g. So if I'm first looking for f composed with g, that means we're going to take our function f and plug in g of x, so we're going to plug in x squared plus 4. And so then from our function f, underneath that radical, we're just going to plug in x squared plus 4. And so now when we start talking about the domain of this new function, the first thing you got to do is just look at whatever you are plugging in. So we first have to look at g, x squared plus 4, and determine whether there are any domain restrictions. So just quickly recall that we are looking for zeros in denominators, or we are looking for radicals or square roots where we can potentially have a negative. But in this case, we don't have either of those two happenings because we don't have a fraction and we don't have a radical. And so specifically for our function g, the domain here is all real numbers. We can plug in whatever x value and it's going to work. So now I go ahead and look at the new composition, the square root of x squared plus 4. And since I have the square root, you do got to watch out for those negatives that could end up inside of that radical. Since we know that g of x has a domain of all real numbers, we have to try that out and test it to see if it works inside of our new function composition. And so we have to decide if we were to plug in all these real numbers into our new function, is that going to work out? And again, since I see that square root, what I'm mainly worried about is ending up with a negative inside of the radical. However, since I have this x squared term, if I did plug in a negative number here, since we're squaring it, it's going to become positive. So then we're going to have a positive number plus 4, and that's always going to give us a positive result. And so no matter what we plug in for this new function, it should end up working out. And so we're going to say that the domain here is also all real numbers. So let's go ahead and take a look at our other composition, g composed with f of x. And we're going to take a look at the domain of that one too. We're going to take our function g and plug in the square root of x, replacing all the x's in g with square root of x. So I'm going to have the square root of x, quantity squared, plus 4. And we can simplify this out a little bit. Since we have the square root of x raised to the power of 2, those actually just cancel each other out, and we're left with x to the first plus 4. Now we got to look at the domain. So here, when we look at x plus 4, which is that composition, it seems like you can use any x value since this is a fairly simple linear equation. But remember, you got to start by looking at whatever you are plugging in. So in this case, the square root of x. And we never want to have negatives inside of the square root of x. So for that part, we're going to say the domain is x values greater than or equal to 0. And we have to proceed with these restrictions in mind. So when I look over at x plus 4 again, we have to take the domain restrictions for f into consideration. So actually the domain for this new composition is just going to be also x greater than or equal to 0. So here's your high-level questioning for this section. We spent a good amount of time talking about composition of functions. And again, that's just taking two functions and creating a new one from it. But for this HLQ, you are given h of x, which is already a composed function. And so your job is to figure out what two functions you can compose together to create h of x, or how is h of x created. And as an extra challenge, can you find a second pair of functions that would work?